So here's our purpose for a little mini lab here. Very simple, okay? In bowling, what's the goal of bowling? You want to try to knock down all the what? The pins here, right? We're going to actually go out to the hallway in a second. We're going to set up a little bowling alley, except we're going to be a little bit weird, okay? You guys ever see how little kids bowl? They have like a little metal track, a little ramp there, so that the kids don't like kill anybody. That's what we're going to do. We're going to use a handicap ramp there, okay? And in real life, you just want to, actually there's a lot of physics in bowling, okay? From the materials of the ball to the angular momentum, all that, but we're going to keep it simple, okay? We're going to find the final velocity of a bowling ball when launched, can't spell right, launched down the ramp in the hallway, okay? The handicap ramp, okay? And so what's weird is you can actually analyze this from a very complex point of view using nifty equations and forces, but what I'm going to show you guys is energy is actually very elegant. So we don't need to write up, procedure, hypothesis, and all that. We just got a very specific problem. So the way we're going to solve this is with our little four-step process using energy, okay? So the first step is let's sketch out what's going on, okay? If you notice in our hallway, rather than building a stairway, I'm exaggerating the ramp. Actually, it's not that steep, okay? To make our school handicap accessible, this is a newer wing of the school, we got a little handicap ramp, okay? And in fact, by law, I bet they have to actually hire some kind of biomechanical physicist so that the ramp's not too steep, et cetera there. If you notice, like, the auditorium, have you seen the handicap ramp by the auditorium? That thing is, like, crazy steep. I think it's probably not up now, because if I was in a wheelchair, I would have a hard time getting up there, okay? So anyhow, we're going to have, in a second, one of you guys, okay, take our bowling ball and just set it up right at the top of the ramp there, okay? So that's supposed to be a bowling ball. I'll sketch that out there. Then, very simply, we're going to launch the bowling ball down the ramp, okay? At the very top, just think about it. What kind of energy do we have stored in our bowling ball system? We have what kind of energy? Potential. We have potential energy. So in fact, the picture is not to waste your time, okay? Because in the end, the math is trivial. It's multiplication, division, addition, subtraction, maybe a square root every once in a while. A little bit of trig, right? Big deal. It's the ideas that are tricky. Let's put it all together. You have potential energy with a little I initially, okay? And now we could also push on the ball, and we could also have the ball moving, right? So what's that called? When it's moving, it's called kinetic energy. And if you push on it, force over distance, that's called what? Work. Let's not do that. That's like a little trickier. We'll do that later on, okay? On some of the practice homework problems. So we could have some kind of work initial, some kind of kinetic initial, some kind of spring or whatever, but we're not going to do any of that. We're just going to have the ball right at the top, and then we're just going to maybe give it a little tap just to get it going down the ramp. But the basic idea is pretty much we're just taking PE and turning it into what at the very end? As it goes down the ramp, all that PE will turn into, if all goes well, what? Kinetic energy, right? That's the whole point. So normally, your bowling alley should be flat, right? So if you're at a bowling alley where the floor is all crooked and or it's at an angle, you probably want to go somewhere else, right? But to make it easy for little kids, they have like those metal ramps. Have you seen them before? And you put them on there and you launch them down. So that way, like, little kid can kind of learn how to bowl, right? Or you don't, you cheat. You got like the little rubber bumpers and all that. Though my little guy still managed to get a gutter ball in the next lane over. Like 2 times we tried to go bowling. So it's like, okay, nobody died, right? And then hopefully you knock over all the pins and all that good stuff there, right? Bam. So anyway, we're going to try to figure out this final speed here at the end. So can you already picture this? At the end, where is all our energy converted to? Our initial potential we put in all goes to what? At the very end. To kinetic, okay? You see that? Now, we could have some kind of potential energy at the end, but why don't we just call this our 0 point? Why don't we call this 0 meters? You know what I'm talking about? So if this is our 0 point here, there is no potential energy. Isn't that kind of nice? And at the end, there might be some kind of work energy, like work done to friction and all that, but we're going to just ignore that for now. We're going to assume that, hopefully, there's very little friction, but we'll find out. And actually, in real life, there is friction, which we'll see big time, okay? So this is just kind of setting up the situation here, okay? And in step 2, what do we do in step 2 in our 4-step problem-solving process? We list all the what? Information, okay? Yeah, this actually helps us figure out what kind of data we need to collect. We actually only need to collect some very basic information. But here's a trick, okay? Before, when it came to projectiles, forces in 2 dimensions, etc., we separated into X and what? Y. For energy, you want to separate it into 2 conditions, energy initial and energy final. What do we mean by that? There's always a before and after picture when it comes to energy. Because in step 3, our big idea is very simple, that the energy you put into a system is the energy you get out. Okay? So to break down our energy equation, we need to look at our knowns and unknowns. So if you think about it, what kind of energy did we put in at the very start? We already just talked about that, right? We put in some kind of what? Potential energy, right? And we could have had kinetic energy. We could have had work energy. But we're actually not going to do that, okay? And at the end, we could have some kind of potential energy, some kind of kinetic energy, and some kind of work energy. But really, we're not going to lift the ball. We're just going to look at it at the very bottom of the ramp, and we're not going to push on it. So this is a pretty simple energy transformation problem, okay? And if you think about it, if you really want the ball to go nuts, instead of just putting up, there's actually 2 handicap ramps in our hallway. Instead of starting it at the top of the first ramp, we could actually start at what? At the top of the second ramp there, right? And you get a little extra kick there, like a roller coaster, basically, right? How do you know which roller coaster is fastest at Six Flags Great America? The one that's simply the what? The tallest, okay? Which is, I believe still for now, the Raging Bull, okay? It's the tallest ride. When you're at the top of the ride, look around. And you'd be like, wow, I'm pretty high up, okay? So anyway, what kind of information do we need to find potential energy? You guys know the PE equation? Let's write down our little toolbox here, right? PE is going to be equal to what? PE, there's 2 forms, right? It's either weight times height, or it's MGH, okay? MGH is usually what we use, okay? So we need to know the mass of the bowling ball in what? Kilograms, right? We need to know gravity, 9.8 meters per second squared. We don't have to worry about it being negative because we're actually calculating the energy, okay? So it's not a negative energy. It's just that's the gravitational acceleration. And then the height of the ramp in meters, okay? Can we get the height of the ramp when we go outside into the hallway in a second? We can, right? We just got to take a meter stick and determine this height difference right here, okay? So what's interesting about a ramp, if you think about it, is it's actually just an energy machine, which you don't really think of. The goal of a handicap ramp is to help somebody, like in a wheelchair or with crutches or whatever, to get from a lower point to a higher point. So if you think about it, when you come into the school, that's a good example. You could either take the stairs on the right-hand side, or you can go up the ramp on the left-hand side. Most people just go up the ramp. The end goal is the same. You raise your potential energy. You go from the ground level into the top of the ramp, whatever, into the hallway, right, of the school there. See that? So really, both people, theoretically, they do the same amount of work, whether you take the handicap ramp or you take the stairway. What the ramp does is it spreads your workout over a bigger distance. So if you think about it, is it easy to roll a wheelchair up to like the stairs and try to throw your wheelchair up 3 stairs? Probably not, right? But can you push it along a ramp? Of course you can, okay? So anyway, we need to go get MGH to get our potential energy. And at the end, we're going to try to find what? What was the goal of our little mini lab? We're trying to find the what? The final velocity, okay? And that's because we're going to set the initial velocity to what? Big fat 0, right? We're not going to have the ball move. We're just going to have it roll down the ramp. That's all. So we're going to find the final velocity, okay, by using energy. So how could we find the final velocity if we didn't want to use energy? We just could use a nifty equation, but that's actually tricky because we'd have to figure out the acceleration on this ramp, which we could do. But then when you have something on a ramp, it's accelerating, so you have to then tilt your reference frame, right? Then you have to find the force parallel. It gets really ugly, right? But energy is going to be really elegant. How come? Because PE is what? PE is MGH. And how do you find KE? You guys remember? KE is real easy. 1/2 mv squared, okay? So we can actually just set, this is MGH initial. I should make this H initial. There we go. What's the height final? Height final is what? 0. There we go, okay? Is equal to 1/2 mv squared final. Hey, look what's kind of cool, actually. What actually happens? What cancels out? You guys see that? The what? The mass of the ball actually cancels out. Isn't that kind of cool? So actually, I don't even really need to know the mass of the ball. Okay, I think it's a 16-pound ball, which is around 8 kilograms. So we don't even need it. It's going to cancel out. So in other words, what's going to fall faster, a heavy object or a light object? You guys remember? Same, right? If you ignore air resistance, right? So what's kind of neat is when you design a roller coaster, theoretically, the mass actually doesn't even matter. So when we go to Great America in May, okay, what's really cool is when you're standing in line like for Batman, time it when you're waiting. A bunch of people get on, a bunch of people get off. 47 seconds, okay? A bunch of people get on, a bunch of people get off. 47 seconds, okay? A bunch of football players get on. The whole team goes, right? They get off. 47 seconds. Bunch of midgets from Minnesota at a convention. Sorry, don't mean to offend any midgets from Minnesota, okay? Whatever. Get off. 47 seconds, theoretically, okay? Real life friction makes small difference, but for such a large machine, it's pretty trivial there, okay? So in other words, all we need to really measure is the height of the ramp. But let's go ahead and measure the velocity of the ball for real. How can you find the velocity of the ball for real? How do you find this speed at the end? Velocity is just a fancy word for speed. All you need is the what? The distance, right, over the time. So why don't we set like the pins maybe like 5 meters away, and then we'll just time it really quick. And then this will be our velocity actual, okay? Maybe I'll put a little whatever, actual here, our actual velocity. And then we'll compare it to our ideal final velocity. And we'll see how the energy calculation compares there. And we could find a little percent difference there, okay? But what I want you to see is energy conservation is a very elegant way to look at and analyze complex situations. Because in real life, a coaster is not just a simple ramp, right? It's crazy. You got loops, boomerang, turns. You got what's called a hyperturn. Raging Bull is a hyperturn, where if you're on the very edge, okay, it's really cool. If you look down, there's actually no track below you. It's a lot of fun, okay? But energy makes a really nice, easy way to analyze it. So we're going to head out in the hallway. We're going to have you two guys do our little bowling ball pin setup there. And then we'll just measure out, let's say, 5 meters from the bottom of the ramp, and we'll time it real quick, and then we can plug and chug. Let's rock and roll. Let's do it. The ramp. The height of the ramp we measured to be 70 centimeters, which is 0.7 meters, okay? And all I do is I just measure from that brick line there. So it's about 0.7 meters, okay? And obviously, the higher the ramp, the more PE you store up. So when we had Mitch ride the skateboard down just for fun, obviously, since he was at the second ramp, he's going to go faster, right? That's all. Good. And then we can actually find the final velocity. That's all we need, right? But to compare, we had Jay time it for us 5 meters, okay? So actually, you know what? Let's find this actual velocity really quick. I need a little bit more room, so I'm just going to zoom out, okay? So really quick, we can find the velocity by taking our delta x 5 meters. And what'd you time that to be? How many seconds? It was 1.6 seconds. If you can get out your calculator really quick, just do 5 over 1.6. If we take 5 meters that the ball rolled from the end of the ramp to the bowling pins, and we divide that by 1.6 seconds, we get a final velocity of about 3.125 seconds. There you go. Oh, you okay? 3.125 meters per second. Do as I say, not as I do, okay? And this was the actual speed that we had Jay measure. We're going to look at the theoretical speed, okay? So we can just plug and chug into our energy equation. Big idea is the energy you put in is the energy you get out, okay? So we took the bowling ball to the top of the ramp. We stored up potential energy. If you think about it, all of life is taking energy from one form to another, right? So we can find P by doing MGH. The M's cancel out, so we just take G, which is, 9.8 times the initial height of 0.7 meters. Don't even put in units till the very end, okay? Because as long as all your units are consistent in step 2, I find that the units, they clutter up the equation, okay? And I know some science teachers don't like that, but just from experience, you guys are a lot more successful once you get all your units consistent, okay? Then we just take 1/2 and then mv squared. M cancels out. We can find the final velocity, okay? How do we do this? We do a little algebra. We multiply both sides by 2. And then how do you get rid of this squared thingy, right? You take the square root, right? So the square root of 2 times 9.8 times the height, you see that, of 0.7. So it's actually a little shortcut equation. Square root of 2gh, if you have no other initial energy, will give you your final velocity, okay, when you convert PE purely to KE. And I'm getting about 3.7 meters per second is my ideal final velocity, okay? So notice, why is the actual velocity less than the ideal one? Because in real life, what do we totally ignore big time? We ignored friction, okay? There's this missing part. That difference in speed is the energy that was lost to friction. So in fact, why don't we find that percent difference really quick, okay? And that will be the energy that was lost to friction. Make sense? And in fact, in real life, you can actually hear it when a bowling ball is rolling and sliding and all that. And actually, there's one other thing too. There's what's called rotational kinetic energy. And for a bowling ball, that's actually big. And we could try to calculate that measure. We're not going to worry about it. We're just going to look at the percent difference of the energy lost there. And all it is to find percent difference, you take the ideal value, right? Subtract it from the actual, and then divide it by the ideal, right? and then turn that into a percentage. That's all. So in other words, okay, the ideal value was 3.7. We got the actual to be, what, 3.125, and then we'll just divide that by 3.7 times 100, right? So let's just do that really quick. If I take 3.7 minus the ideal speed, right, the actual speed, 3.125, and then I divide that by the ideal speed, and then multiply that by 100, looks like we're off by about 15%. So that means there's, whatever, about 15.6, whatever, 5, but we'll round that off to 16%, okay? There's about 16% difference between the ideal value we calculated and the actual speed that we measured, okay? And all that is it's energy that was lost to friction, sound energy, rotational energy, etc. You see that? But what's nice about this is it's a very elegant way to find the final speed if you had a very complex track. Because in the end, the only thing that matters is what's that final height. Okay? So in a nutshell, to summarize, by applying the conservation of energy, we could analyze a very complex situation, which we will. We're gonna up it up, ramp it up a little bit. Ha, no pun intended. Where you'll have a skateboarder pushing on the ground, so you're doing work, you have potential energy, right? You're moving along, you have kinetic, and then you fly down a ramp in a half pipe and whatever. And at the very end, we can actually figure out exactly how fast